Hello students, welcome to this new video lecture on the topic thermodynamics. This is given in chapter number 12 of Physics for Class 11 of NCERT syllabus. In today's session, I will first introduce the topic thermodynamics, followed by thermal equilibrium, zeroth law of thermodynamics, heat, internal energy and work, as well as first law of thermodynamics. We will end today's session with description of specific heat capacity, which was also given in chapter number 11. In chapter number 11, we have studied thermal properties of matter, whereas in this chapter we shall study laws that govern thermal energy. We shall study the processes where work is converted into heat and vice versa. As you know, when we rub our palms in winter together, we feel warmer. Here, the work in rubbing produces the heat. Conversely, in yet another case of a steam engine, the heat of steam is used to do useful work in moving pistons, which in turn rotate the wheels of train. In physics, we need to define the notions of heat, temperature, work, etc. more carefully. Historically, it took a very long time to arrive at the proper concept of heat. In modern times, heat is described as a form of energy, and the experiment demonstrated conversion of energy from one form to another, that is, from work to heat. All this we will study in this very interesting topic, thermodynamics. Please note down the important points narrated by me, as the same will help you in your examinations. So I welcome you once again. Introduction. Thermodynamics is the branch of physics that deals with the concept of heat and temperature and interconversion of heat and other forms of energy. So thermodynamics is a branch of physics that deals with concepts of heat and temperature and conversion of heat and other forms of energy. Thermodynamics is a macroscopic science. It deals with bulk system and does not go into the molecular constitution of matter. In fact, its concept and laws were formulated in 19th century, much before the molecular picture of matter was firmly established. Thermodynamic description involves relatively few macroscopic variables of the system, which are suggested by common sense and can be usually measured directly. So this is a very simple chapter. In contrast, a microscopic description of gas, for example, would involve specifying the coordinates and velocities of huge number of molecules constituting the gas. The description in the kinetic theory of gases is not so detailed, but it does involve molecular distribution of velocities. Thermodynamic description of a gas, on the other hand, avoids the molecular description altogether. Instead, the state of a gas in thermodynamics is specified by macroscopic variables such as pressure, volume, temperature, mass, and the composition that are felt by our sense perception, and these are measurable. So in thermodynamics, we deal with macroscopic variables such as pressure, volume, temperature, and mass. Thermodynamics is a branch of science which deals with exchange of heat energy between bodies and conversion of heat energy into mechanical energy and vice versa. Before we go into the details of theories of thermodynamics, I will just introduce few terms that are very frequently used in thermodynamics. Of course, some of these terms will be dealt in detail in subsequent slides. So, what is a thermodynamic system? A thermodynamic system is a collection of extremely large number of atoms and molecules confined within certain boundaries such that it has certain value of pressure, volume and temperature. Though we deal with a large number of atoms and molecules, but these things are responsible for producing pressure, volume and temperature, which are studied in thermodynamic system. Anything outside the thermodynamic system to which energy or matter is exchanged is called its surroundings. So anything outside the thermodynamic system is surroundings. Types of thermodynamic systems. Open system. In open system, there is an exchange of both energy and matter with the surrounding. Whereas in the closed system, the exchanges only the energy, not matter, with the surrounding. So, in closed system, we exchange energies. In an isolated system, it neither exchanges the energy nor matter with the surrounding. So, please repeat: open system, closed system and isolated system. Thermodynamic variables. The thermodynamic variables are pressure, volume, temperature, internal energy and number of moles, and these are called thermodynamic variables. Thermodynamic, there is yet another term, thermodynamic state variables. Please note state variables. A state variable is a property of a system that depends only on the current equilibrium state of system and thus does not depend on the path by which system is arrived at its present state. Example: internal energy, enthalpy and entropy. These we will learn in subsequent, probably the end of this chapter, about the enthalpy and entropy. Internal energy, of course, we will learn in this session itself. Then there are intensive variables like pressure and temperature, and extensive variables which indicate the size of the system. Example: mass and volume. Thermal equilibrium. Please examine the figure in A. Here, the figure A, the systems A and B, two gases, that is separated by an adiabatic wall, that is an insulating wall. This black colored is a insulating wall between A and B, and an insulating wall does not allow the flow of heat. Whereas in figure B, the insulating wall of figure A is replaced by a conducting wall between A and B as shown in the figure. The same systems A and B separated by a diathermic wall. The conducting wall is also called a diathermic wall, a conducting wall that allows heat to flow from one to another. In this case, the thermal equilibrium is attained in due course. So in thermodynamics, we say that a state of system is an equilibrium state if the macroscopic variables that characterize the system do not change in time. For example, a gas inside a closed rigid container completely insulated from its surroundings with fixed values of pressure, volume, temperature, mass and the composition that do not change with time is in a state of thermodynamic equilibrium. So, a rigid container, if there is a rigid container very closed so that it is insulated from its surroundings where with fixed values of pressure, the pressure is fixed, the volume is fixed and the temperature is fixed and mass is also fixed. There are no changes, and composition that do not change with time. The composition will not change, and this is in thermodynamic equilibrium. In general, the state of equilibrium depends on surroundings and the nature of the wall that separates the system from the surrounding. So we may not have a perfectly isolated system. So in general, the state of equilibrium depends on the surroundings and the nature of the wall that separates the system from surroundings. Zeroth law of thermodynamics. Consider two systems A and B separated by an insulated wall between A and B and a conducting wall between C and A and B as shown in the figure. The states of system will change until both A and B come to thermal equilibrium with C, because A is in contact with C, B is also in contact with C. After this is achieved, suppose the insulating wall between A and B is changed, is replaced by a conducting wall, and C is insulated from A and B by an insulating wall as shown in figure B. Please see here, there is in figure B, there is an insulating wall between C and A as well as C and B, whereas conducting wall between A and B. Hence, it is found that the states of A and B change no further. They are found to be in thermal equilibrium with each other. This observation forms the basis of the zeroth law of thermodynamics. R.H. Fowler, scientist, formulated this law, that is the zeroth law, in 1931, long after the first and second laws of thermodynamics were stated. We will study about the thermodynamics first law and second law in subsequent slides in this chapter itself, but in later part of part 1 and part 2. Whereas the zeroth law was formed after first law and second law. The zeroth law of thermodynamics states that two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. That is, two systems A and B in thermal equilibrium with a third system C separately are in thermal equilibrium with each other. Each other here means A and B. The zeroth law clearly suggests that when two systems A and B are in thermal equilibrium, there must be a physical quantity that has the same value for both. That means The physical quantity here is a temperature. So temperature of A and temperature of B will be same. This thermodynamic variable whose value is equal for two systems in thermal equilibrium is called temperature, capital T. Thus, if A and B are separately in equilibrium with C, then TA is equal to TC and TB is equal to TC because they are in contact with one another. Therefore, it implies that TA will be equal to TB, that is, the systems A and B are also in thermal equilibrium. This is zeroth law of thermodynamics. Heat, internal energy, and work. We know that every bulk system comprises of a large number of molecules. Internal energy is simply the sum of kinetic energies and potential energy of these molecules. Consider a large number of molecules in a box. The internal energy, capital U, represented by a symbol capital U, of a gas is the sum of kinetic energy and potential energy of its molecules when the box is at rest. Kinetic energy, due to various types of motion, that is motion, translational, rotational and vibration, is to be included in the kinetic energy. In yet another case, if the box containing molecules is moving as a whole with some velocity, the kinetic energy of the box is not to be included in the internal energy. So, internal energy is thus the sum of molecular kinetic and potential energies in the frame of reference related to which center of the mass of the system is at rest. As I stated earlier, the box was at rest. Thus, it includes only the energy associated with random motion of molecules of the system. We denote the internal energy by of a system by letter capital U. The important thing about internal energy is that it depends only on the state of the system, not on how the state was achieved. So, internal energy of a system is an example of a thermodynamic state variable. Its value depends only on the given state of the system, not on the history. That is, it does not depend on the path taken to arrive that state. This is very important characteristics of an internal energy, that it does not depend on the path taken to arrive at that state. Thus, internal energy of a given mass of gas depends on its state described by specific values. So, the internal energy depends of a given mass depends only on specific value of pressure, volume and temperature. It does not depend on how this state of gas came about. Pressure, volume, temperature and internal energy are thermodynamic state variables of the system, that is gas. If we neglect the small intermolecular forces in a gas, the internal energy of a gas is just the sum of kinetic energies associated with various random motion of its molecules. Here, we neglect the small intermolecular forces. Hence, potential energy is neglected and only it is the sum of kinetic energies associated with the motion of its molecules which are moving in at random. Heat and work energy. Heat and work are two distinct modes of energy transfer to a system that results in change in its internal energy. That means if we heat a body, the molecules gain the energy and thus heat is transferred to a internal energy. Please see the figure here. Energy is transferred due to temperature change. This container having a gas molecules with a piston, when it is heated, the molecules gain the heat energy and its internal energy increases. So consider a system containing certain mass of gas in a cylinder. This is a cylinder with a movable piston. This is the piston as shown in the figure, and it is containing a gas. There are two ways of changing the state of gas. Two methods. Hence, changing the state of gas means it's changing its internal energy. One is put the cylinder in contact with a body at a higher temperature. That means you heat it at the bottom, and that heat, the temperature difference between the gas molecules and the surrounding will cause the flow of energy from the outer body to the gas, thus increasing the internal energy of the gas. The energy of the gas increases because of this heating at the bottom. The other way is we can push this piston down to do the work. That is, you compress the gas, do the work on system, which again results in increasing the internal energy of the gas. See, internal energy of gas can be the internal energy of the gas can be increased either by heating or by pushing it mechanically so that it is compressed and its internal energy increases. Both these things could happen in reverse direction. It can also happen in reverse direction. Heat it, it gets energy and it can push it outer. With the surroundings at a lower temperature, heat would flow from the gas to the surroundings. Likewise, the gas could push the piston up and do the work on the surroundings. So the gas can also push the cylinder. Thus, to summarize, heat and work in thermodynamics are not state variables. They are modes of energy transfer. So heat as well as work is a mode of energy transfer, but they are not state variable to a system, resulting in the change of internal energy, which is a state variable. So heating and doing the work are not state variables, whereas these two result in increasing the internal energy, which is a state variable. Please note that. First law of thermodynamics. The internal energy of a system can change through two modes of energy transfer. As we have seen earlier in the previous slide, the internal energy, capital U, of a system can be changed through two modes of energy transfer, that is by heat and work. Let delta Q equals the heat supplied to the system by the surroundings, and the delta W equals work done by the system on the surroundings, and delta U be the change in internal energy of the system. So the general principle of conservation of energy implies that the heat supplied is delta Q should be equal to the change in internal energy delta U and the work done, change in work done in the system. So it can be written mathematically as delta Q is equal to delta U plus delta W. Let it be equation 1. Thus, the energy delta Q supplied to the system goes in partly to increase the internal energy delta U and rest in work done on the environment. The work done is delta W. So there is an increase in internal energy and also a work done. So heat supplied is equal to increase in internal energy plus work done. And equation 1 is known as this equation delta Q is equal to delta U plus delta W is known as the first law of thermodynamics. It is simply the general law of conservation of energy applied to any system in which the energy transfer from the surroundings or to the surroundings is taken into account. Alternatively, we can rearrange equation 1 as delta Q minus delta W equals delta U. That is rearranging equation. We can write delta Q minus delta W is equal to delta U. Let it be equation 2. Since U is a state variable, delta U depends only on the initial and final states and not on the path taken by the gas to go from one to the other. Whereas delta Q and delta W will in general depend on the path taken to go from initial to final states. From the first law of thermodynamics, it is clear that combination of delta Q minus delta W is, however, path independent. This shows that if the system is taken through a process in which delta U is equal to 0. For example, isothermal expansion of an ideal gas. This we will study in the next section, probably section 12.10 or 12.12, where delta Q is equal to delta W. That is, heat supplied to the system is used up entirely by the system in doing the work on the environment. This is the first law of thermodynamics. Application of third law of thermodynamics. If the system is a gas in a cylinder with movable piston, the gas in moving the piston does the work. So consider a system containing a gas in a cylinder with a movable piston as shown in the diagram of earlier slide. The gas is in moving the piston does the work. Since force is a pressure times area and area times displacement is volume, the work done by system against a constant pressure is delta W is equal to P into delta V. That is, pressure is a constant. If pressure is kept constant, the work done is equal to change in work done is equal to change in volume. Delta V is the change in volume, where delta V is the change in volume of the gas. Thus, case of equation 1 gives in the previous slide that delta Q is equal to delta U plus P into delta V, because earlier we had written it as delta U plus delta W. Here we are substituting delta W by P into delta V. Let this be equation 3. Now consider an example. Consider the change in internal energy for 1 gram of water when we go from its liquid to vapor phase. The measured latent, we know the latent heat of water is 2256 joules per gram. That is, for 1 gram of water, we require delta Q equals 2256 joules of latent heat. Therefore, at atmospheric pressure, 1 gram of water has a volume 1 cubic centimeter in liquid phase, and when it becomes gas, its volume is 1671 centimeter cube in vapor phase. Therefore, delta W is equal to pressure into change of volume is volume of gas minus volume of liquid state. So that can be written as pressure is 1.013 into 10 to the power of 5 and change of volume is 1671 into 10 to the power of minus 6. That is difference between the two volumes. That is equal to 169.2 joules. Equation 3 then gives delta U is equal to change of internal energy is 2256 minus 169.2. Therefore, that is equal to 2086.8 joules. We see that most of the heat goes to increase the internal energy. Hence, internal energy is increased energy of water in transition from liquid to vapor phase. Specific heat capacity. This chapter is given in chapter number 11 as well as it will be covered in chapter number 12. The details of specific heat capacity and its theory and applications were already explained in chapter number 11.6. I will not explain it again. However, the text part is repeated here for your information. Heat capacity of the substance is capital S is equal to delta Q by delta T. That is, the specific heat capacity equals change in quantity of heat divided by amount of heat supplied divided by change in its temperature. And there is yet another system, specific heat capacity, represented by a letter small s, that is equal to small s, capital S by m. So that is 1 by m into delta Q by delta T. There is yet another system called molar specific capacity, which is applied in the case of gases. So, and it is represented by the symbol capital C, that is equal to, that is definition is C is equal to small s by mu, where mu is the moles, number of moles mu. That is equal to, that can be written as 1 over mu into delta Q by delta T. Please go through the link. This explanation and this chapter is given in the link in the description part of this video. Please go through it. So the specific heat capacity of gases has got two types. One is at constant volume or a pressure volume. So when the pressure is kept constant, the specific heat capacity, that is molar specific heat capacity of gases, is Cp. On the other hand, if there is a constant volume, the molar specific heat capacity is capital CV is represented by letter Cv. Hence, if the volume of the gas is maintained constant during heat transfer, then the corresponding molar specific heat capacity is called molar specific heat capacity at constant volume. Please go through the link in the description part. Similarly, just to compare the specific molar heat capacity and the normal specific heat capacity, the comparative parameters are given in table 1, which indicates specific and molar heat capacity of some of the solids at room temperature and pressure. These values are also given in the in section 11.6.1. Just note here, there is a vast difference. The specific heat capacity is expressed in joules per kg per Kelvin, whereas molar specific heat capacity is expressed in joules per mole per Kelvin. The difference in values can be seen are very fast. And yet another is the molar capacity, specific heat capacity of gases. Please see here the values of Cp, that is molar specific heat capacity at constant pressure. This P indicates constant pressure. Expressed in joules per mole per Kelvin is of the order of 20.8 for helium and all that, and the value of Cv, that is the specific heat capacity at constant volume, which is expressed in joules per mole per Kelvin, also is shown. The difference is the Cp is always, please note from this table, Cp is always greater than Cv. We'll continue our discussions of specific heat capacity by explaining additional concepts pertaining to the gas. The amount of heat absorbed or evolved by unit mass of a substance such that its temperature changes by unity is called the specific heat capacity of the substance. Sometimes we say it is specific heat capacity or specific heat. We avoid the word specific capacity. The specific heat capacity is expressed as Q is equal to Ms into delta V, where Q is the amount of heat supplied, M is the mass, S is the specific heat, and delta T is the change in temperature. This delta T can be expressed as final temperature minus initial temperature, that is Ms into Tf minus Ti. Let it be equation 1. Therefore, specific heat capacity can be defined as S is equal to Q divided by M into delta T. Let it be equation 2. Consider a solid of n atoms, each vibrating about its mean position. If Kb is a Boltzmann constant, we can write that if an oscillator is one dimension, the average energy is given by the relation 2 into 1 by 2 kb into T, that is applying Boltzmann constant. That is, the oscillator has an average energy is kb into capital T, where kb is the Boltzmann constant. Therefore, in 3 dimensions, it can be written as 3 into kb into capital T. For a single mole of a solid, the total energy is capital U is equal to 3 kb into T into N into A. That is in the number of atoms. Na is the number of atoms. Therefore, this kb into T into Na is nothing but the gas constant represented by the symbol capital R. Hence, the total energy U is 3 into RT. Let it be equation 3. Now at constant pressure, delta Q is equal to delta U plus P into delta V. that is approximately equal to delta U, because for change in volume delta V, that is change in volume, is negligible in case of solids. Hence delta Q will be equal to delta U. Now we define molar specific heat, capital C. As explained earlier, it is delta Q by C is equal to delta Q by delta T. That is delta Q is delta U here divided by delta V. That is equal to 3R from equation 3, because delta V is 0. So let it be equation 4. This is valid at room temperature with carbon as an exception. So this is not applicable. Carbon does not obey this law. Therefore, C is equal to 3R. Specific heat capacity of water. Let us take a special case of specific heat of water. The old unit of heat was calorie. 1 calorie was earlier defined to be the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade. Please see the figure on the screen. Here it shows the variation of specific heat capacity of water with temperature. As we increase the temperature, the specific heat, that is calories per gram in degree centigrade, that is it decreases initially up to 40 degrees and then it raises. Temperature, this is up to 100 degrees, that is 0 degrees to 100 degrees. The graph is shown on the screen. The old unit of heat was calorie. 1 calorie was earlier defined to be amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. That is, calorie means one, that is required, the amount of heat required to change the temperature of 1 gram of mass of water by 1 degree Celsius. Now 1 calorie is defined to be amount of heat required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. Now we will explain the relationship and we will prove the result PV equals RT. That is the relation between specific heat at constant volume and pressure. What is the relation between Cp and Cv? That is Cp minus Cv is equal to R has to be proved. To prove Cp minus Cv is equal to R. The specific heat capacity depends on process or the conditions under which heat capacity transfer takes place. So heat capacity, specific heat capacity depends on the process or the conditions under which heat capacity transfer takes place. Therefore, for gases, we can define two specific heats. As explained earlier, there can be specific heat at constant volume as well as specific heat at constant pressure. So, for an ideal gas, we have a simple relation Cp minus Cv is equal to R. This is the equation, relationship between Cp and Cv, that is equal to R. It is a Cp and Cv are molar specific heat capacities of ideal gas at constant pressure and volume, and R is the universal gas constant. So hence Cp minus Cv equals R. Let it be equation number 5. To prove the relation, we begin with equation delta Q is equal to delta U plus P into delta V, where delta Q is the amount of heat and delta U is the change in internal energy, P is the constant pressure and delta V is the change in volume for 1 mole of gas. So if delta Q is absorbed at constant volume, that is, if we keep the volume constant, change in volume is 0. Therefore, delta V equals 0. Therefore, Cv is equal to, that is specific, molar specific heat at constant volume is delta Q by delta T at constant volume, that is equal to delta U by delta T. Because here in this case delta Q is equal to delta U, that is equal to delta U by AT. Simply we have avoided the representation of constant volume. Let it be equation 6, where the subscript V is dropped in the last step, since U, that is internal energy of an ideal gas, depends only on temperature. If on the other hand delta Q is absorbed at the constant pressure, that is, previously we had seen constant volume and now we will take up constant pressure. That is, Cp is equal to delta Q by delta T at constant pressure, that is equal to delta U by delta T at constant pressure plus P into delta V by delta T. Here there is a change in volume at constant pressure. There, let it be equation 7. So here we can also avoid the subscript P can be dropped from the first term, since the internal energy of an ideal gas depends on temperature only. That is, the first term on the right hand side, you can drop the letter subscript P of equation 7. Therefore, for a 1 mole of ideal gas, PV is equal to RT. That is the equation we know. Therefore, which gives P into delta V by delta T at constant pressure is equal to R. Let it be equation 8. Hence, the equation number 6, 7, if we subtract Cp minus Cv, we get the desired equation. Equation number Cp minus Cv is equal to R. This is to prove that Cp minus Cv is equal to R. This is the equation 5 is proved here. This is the relation we have proved. With this, we come to the end of part 1 of thermodynamics. Next lecture, we will explain the concepts of thermodynamic state variables and equation steps, equation of state, and thermodynamic processes, heat engines, refrigerators and heat pumps, etc. etc. Till then, goodbye. Please revise whatever I have explained in today's lecture. Thank you.